Okay, so based on some feedback with some students, I thought I'd give some hints for this homework. This homework is going to be due the December 10th for a resubmit. So I want you to resubmit this homework, and I'll give you some hints for that. And there will be one additional assignment that will be due later after that. So let's look at problem 1. I assume you've read this already. So let's look at this first one. Show that the column space of A is spin by V1 through Vm. These are the eigenvectors corresponding to the non-zero eigenvalues. Okay. So I suggest you try a couple of steps here. Okay. So step one would be show that V1 through Vm are in col of A. Okay. They can't span col of A unless they're in col of A. All right. And then, so you can consider A Vj. Okay. And then for problem 2, you want to show they're linearly independent. Okay. And then you want to show that the, how can I say this? The dimension of column A is equal to the number of vectors that you have. All right, you have m vectors. Now, if you have m independent vectors in an m-dimensional space, then that's a basis. So I say m independent vectors and independent vectors, or I should say m linearly independent vectors in an n-dimensional space are a basis. And that's something that we've talked about before. That's a fact of linear algebra. If you have fewer than m linearly independent vectors in an m-dimensional space, they don't span. And if you have more than m vectors in an m-dimensional space, they can't be linearly independent. But if you have exactly m, it's like the Goldilocks theorem. If you have exactly m linearly independents in an m-dimensional space, then that is a basis, and they span the column and they span the column space. Okay. All right. All right. Now for the second problem, I've expressed x in summation notation, and then you simply want to apply a to the k to this vector. Now notice that I've changed the index here because I think that some of the index notation was confusing things. Some of the indices were ambiguous. So I think it's probably better you use a k here. I don't remember what was there before. But this has to be true for every value of k between 1 and m. Okay. So how are you going to do this? So in this case, if I want an expression for a to the k of x, well, I have x here. And then, so here you're just going to apply. All you have to do here is you have to apply a to the k to this expression. And use what you know about a Vj and AW. Okay. Now all a to the k is just you're just applying a repeatedly. So you have to apply a repeatedly. So if you know what a does to Vj, then a to the k is just going to do that k times. If you know what a does to W, then a to the k is just going to do that k times. All right, now let's go down to the next one. Okay. All right, so let's look at this one. So what you want to do is, so you want to write the linear combination as of rows as, well, it's going to be a sum of vectors, so it's certainly going to be something like this, sum. Now, how many rows are there? There are m rows, so this is going to be, I'll use j here, 1 to m, of, so I can say cj, and let me just call this rj, where rj is the jth row. Okay. Okay. Now remember, to show that this is linearly independent, what you need to look at is a linear combination and set equal to 0. So we want to show that this linear combination is only 0 if all the CJs are 0. So we want to show that given summation over j of Cj Rj equals 0 implies that Cj equals 0 for j between 1 and m. That's what we want to show. Okay. So what you want to do here is you want to rewrite this sorry, okay, I don't know how to get rid of this. Okay, we'll do this. Okay, okay, come on. Okay, so this is going to mess up the letters, but that's okay. So I want to rewrite this vector equation as m different equations. Now, in each of these equations, so let me say it this way. All of these equations can be expressed as p of x equals 0 for some value of x. Where, actually, I'll give you the polynomial, p of x is equal to the sum j equals 1 to m cj x to the j. Okay, so here's my polynomial. Remember that we're talking about an nth degree polynomial. So this is my nth degree polynomial. Okay. Okay. Now each equation plugs in a different value of x. Okay. Each equation plugs in a different value of x. So each equation is giving me a different root of p of x. Okay. So each equation gives me a different root of p of x. So that gives me m roots. Okay. Now that's no problem because a polynomial can have m roots if it's an nth degree polynomial. Okay, that's not a problem. The problem comes when I have there's one more root. There's also another root. And this is the key. A lot of people miss this. There's one more root of p of x. So this implies p of x has n plus 1 roots. Okay. Now that's not possible for a non-zero polynomial. The only way this can happen is if the polynomial is a zero polynomial. Okay. Okay. The only way this can happen is if p of x is the zero polynomial. Okay. So the key here is that you have to come up with a polynomial, and you have to tell me what the m plus 1 roots are. If I have m plus 1 roots for this polynomial, then this polynomial must be the zero polynomial. So then explain what this means, what this implies for linear independence of the vectors. Okay. All right. All right. Now, next, use the results of B and C to show that these vectors are linearly independent. So what you want to do now is take advantage of your summation notation. You have an expression for x. Okay. All right. So we're really giving your summation notation a workout. Now, I want to say something here before I forget is be careful in your sums about indices. Okay, both you have to be careful about the upper index of your sum and the indices of the different terms have to match. Okay, so for instance here, this number here, that's important. Don't just write sum with no limits. The limits are important. You have to tell what they're through. These indices have to agree properly. Right? If I put an m here, that's not correct. Make sure that your indices make sense. There's a difference between a limit index and a running index. This j is a running index. It does not have a fixed value. It takes values from 1 to m. Some of these indices are running indices, some are fixed. The ones that are fixed are the ones that are given in the problem. For instance, here, I know I have an mth degree polynomial. So this m is a fixed number. It's not a running index. The j has no fixed value. It can take any value from 1 to m. Okay? So I hope that makes it a little bit more clear the difference between a running index. Sometimes they call them dummy indices. This j, because it doesn't have a fixed value, it's only used for the purpose of the sum. Okay? Okay, and the indices within the sum have to match correctly. So you have an expression. You have an expression for m in terms of sums, as a sum. Okay, you can apply a. Well, here, since a runs from 1 to m, I would apply a to the j to that expression. And then use the summation from j equals 1. Now, how many are there? There are m of these. Now, the dj times a to the j x equals to 0. Okay. Okay. Show this implies that the DJs are equal to 0 for j between 1 and m. Okay. Okay. You need to show that these are 0. Okay, and that implies that these vectors are linearly independent. Just like we showed up in the previous problem. If we have a linear combination, and the only linear combination that gives you 0 is the trivial linear combination, that means that those vectors must be linearly independent. Okay, let's look at the next one here. Okay, so the next one says normalize the vectors, and you're going to be writing these as summations. So you'll be writing, well, a to the jx. It's actually going to be a summation of vectors on the top. I'm not sure what coefficient there is. I'll just put a coefficient aj. You can figure out what that is, where j goes from 1 to m. And then on the bottom, you're going to be normalizing. So you're going to divide by the norm of this. So you divide by this norm. Okay. All right, so here you have m terms. Okay. And the question is, which terms have the largest coefficients? Okay. The corresponding v's will be the most important. Or I can say will dominate or predominate in the vector. Or I say in the sum. And the v's with small coefficients will make little contribution. Okay. So the question is, which v's are making the largest contribution to these vectors in your subspace? And those are going to be the vectors that span your subspace, because they're the ones, the other ones are making very little contribution. All right, so I'm going to stop here. I hope this will help some. And we'll also be talking if I haven't talked with you already.